Okay, so now we're doing video 2. So I'm on page 2 on this one. I'm going to proceed without a calculator on these. Okay, because we got to be able to recognize these without doing or using a calculator. All right, so if I look at each one of these, ace of our first term in this, if I plug in 1, is going to be negative a half. What's our next term? If I multiply by, if I square this or multiply by negative 1/2 each time, I'm going to get 1/4, then negative 1/8, then positive 1/16, then negative 1/32. Okay, so it is alternating because we're multiplying by a negative number each time. But I want you to look at these. If we were to graph this, they'd be going positive, negative, but each of them is getting smaller and smaller and smaller. So what will they eventually approach? Well, the limit of a sub n in this case, as n approaches infinity, doesn't matter, it's going from either side, it's going to approach a single value as these get smaller and smaller, and that's going to be 0. Okay? If you look at the graph, you'd see the same thing, and it would be jumping up and down, but each side, each time it gets closer and closer to that x-axis. Okay, so the next one, whatever you see one of these, you got to plot them out. There's no way around it. Okay, so when n is 1, it's just the cosine. And when n is 1, I get of 3 pi over 4. Okay? The next one is going to be the cosine squared. And when I plug in 2, I get 8 minus 1 is 7 pi. So it's really 7 pi over 4. And then we're going to square that. My next term is going to be the cosine of, it's 12 minus 1 is 11 pi over 4. And I'm going to cube that. So I'm going to probably do 4 of these. And then, so if you look at this, it's just going up by 4. That's why, since it's 4n, so it's going to be 15 pi over 4 to the 4th. Okay, so if we think of what is the cosine of 3 pi over 4, well, that's down here, right? Right, because here's 1 pi over 4, 3 pi over 4 is over here. Whoops. So that's 1 pi over 4, 2 pi over 4, 3 pi over 4, and the cosine of that is going to be negative root 2 over 2. Okay. 7 pi over 4 is going to bring us over to here, okay, which is going to be it's still root 2 over 2, but I'm now going to square it, okay? All right, 11 pi over 4 brings us back to here, okay? Because each pi over 4, or 4 pi over 4, is really adding pi each time, if you really think about it. So that is going to be negative root 2 over 2 cubed. And then what's our last one? Brings us back down here, which makes it positive again. And that's going to be root 2 over 2 to the 4th power. Okay, so if you look at this each time, it is geometric. Okay, and what are we multiplying by? Okay, what are we multiplying by? So our first term we know is negative root 2 over 2. And what's r equal to? Well, r is equal to, well, what am I multiplying by each time? Is negative root 2 over 2. Okay. So will this reach a single value? As we keep, well, what are we multiplying by each time? Well, root 2 over 2 is 1.41, okay? Root 2 over 2 divided by 2 is about 0.7, so it's negative 0.7. We are getting smaller and smaller and smaller each time. So when you multiply by a number it's between negative 1 and 1, what does that mean? Each of these is getting smaller and smaller, so what will that limit as n approach infinity equal? Of a sub n is it's going to equal 0. Doesn't hit there initially, but it's just like the one up here, is if r is between negative 1 and 1, it's going to reach a single value. And since it was between negative 1 and 1, it's going to approach a single value, which is, of course, going to be... What? What did I hear? Is it's going to be 0. Okay? So it will equal 0. Now, if it were a series, we would actually have a sum. Okay, and it would converge to a single value. Why? Because we're eventually adding 0. Does that always happen? No, but only when it's geometric. Okay, so the next few I'm going to look at are, now we're going to start talking about indeterminate limits. And there are many limits that we cannot determine by direct substitution. And this is going to bring us into what's called L'Hopital's rule, and I always say L'Hopital. Okay, that's how I emphasize it. It's not Hospital's rule, it's L'Hopital. Okay, so if you look at this one, if I do a direct substitution and I plug in infinity, well, the natural log of infinity is infinite, divided by infinity, well, that's indeterminate. Okay, I cannot compute a single value. You may say, well, isn't that equal to 1? Not necessarily. Some cases it may be, other cases it may not be. Okay, so now if I look at the next one, the limit as x approaches 0. What do I get as x approaches 0? Well, that's 1 minus 1, and I get 0 on the bottom, so I get 0 over 0, which is also indeterminate. Okay, I cannot determine a value, at least by the methods that we have at this point. Okay, now if I look at number 3 and I look at the limit as n approaches infinity on this one, I'll zoom in a little bit. Well, that bottom becomes positive infinity, or the top becomes positive infinity. As x goes to negative infinity of e to the negative x, well, the two negatives make it positive, so it's e to the infinity, which is still what? Infinite. So I have infinity over infinity. We don't know which one's growing faster. We may have some methods we can determine that is, but these are all indeterminate. And I want you to look at this one. As n goes to, or as x goes to infinity on number 4, well, this goes to 0, because remember, e to the x, negative x, looks like this. So as x goes to infinity, that may have helped us here too, as it went to negative infinity, as it went all the way to positive infinity. So here, what happens is as I approach positive infinity, it goes to 0. What does this go to? Infinity. But I want to tell you that is not a form we want. So I can actually manipulate this one. So I get the limit as n goes to infinity, or x goes to infinity, of the square root of x over e to the x, because I can write it with a positive exponent. Okay, and now I get infinity over infinity. So these are the cases you want, or if we ever get these, okay, we can use our friend what's called L'Hopital's rule. And we've talked about it, or we've kind of mentally used it in the past, but we have not actually computed values. Okay, so really what we're looking for is, I would actually not include these. It's really 0 over 0, or infinity over infinity, or negative infinity over negative infinity. If we get that, we can use what's called L'Hopital's rule when we get one of these forms. If we don't get one of these forms, it says, no, you cannot apply L'Hopital's rule if it's not one of these forms, but we may be able to transform it to one of these forms. And that's why I did that on number 4, because this is not one of those forms. You have to have 0 over 0 or infinity over infinity in order to apply it. Okay, what is L'Hopital's rule? Okay, L'Hopital's rule says we're going to let f and g be continuous functions that are differentiable on an interval containing c, except possibly at c. So it may not be differentiable there, but the limit still exists. Okay. If the limit produces one of these, then we rewrite it as L'Hopital's rule says we're going to take the limit of the derivative of f over the derivative of g. Okay, so really, in this case, this was f, this was g. Okay, so it's not the quotient rule, it's the derivative of the top divided by the derivative of the bottom. And if that approaches a value, that is our limit. Okay, however, if that is indeterminate, then I go apply it again. I take a derivative of the top, the derivative of the bottom, provided the limit exists or is infinite, and until I can actually compute a value. Why does this work? We are looking at the relative rates of change to determine limits. And really what that's saying is which is increasing faster, the top or the bottom, but we need to show some proof on this. Okay, so we're going to do a couple of the examples. I'm going to chop it off after the first 4, I think, okay, on this video. So if you look at the first one, these are the 4 we just did, okay, or 4 of similar ones that we just did. So if I look at this one, we know that in this case, we got infinity over infinity. And if you remember, our cases that we can use it for infinity over infinity, or plus or minus over plus or minus, or 0 over 0. As long as it meets that, and you must show this, we can apply L'Hopital's rule, which is going to say the limit as x goes to infinity of, well, what's the derivative of the natural log of x? Well, it's 1 over x. Okay, the derivative of the bottom is just 1. Okay, so now if I look at this, well, the limit as x goes to infinity of the top, ooh, that's taking 1 and dividing it into an infinite number of parts. How big is each part going to essentially be? Is going to be 0. Okay, so what is that saying? Well, which one's growing faster? Isn't that telling us the bottom one's actually growing faster? Okay, they look to be infinite, but when we start looking at the relative rates of change, which was this, we were actually able to compute a value. Okay, so let's look at the next one. So we computed before that we got 0 over 0, so I therefore can apply L'Hopital's rule. Okay, I got to verify it with this, and you notice I don't say equals, I'm using an arrow. It's saying now the limit as x approaches 0 of this. Well, what's the derivative of the top? Well, the derivative of this is 0, so I get 2e to the 2x all over 1. Okay, so now if I take the limit as x approaches 0 of the top here, well, if I substitute in 0 there, I'm going to get 2. And what do I get on the bottom? 1. So what is that limit actually equal to? It is 2. So we had 0 over 0, which normally we think of as indeterminate, but when I applied L'Hopital's rule, we were able to determine that its limit is actually 2. Because I started looking downstream as how are their limits changing relative to each other. Okay, so if we look at the next one, I think on this we got infinity over infinity, which tells us I can apply L'Hopital's rule, or I can say L'Hopital. All right, so I'm going to do the limit as x approaches 0 of, well, the derivative of the top is 2x, and the derivative of the bottom is e to the negative x, but I get a negative out front. Okay? Oh, that was as we approach infinity, I'm sorry. And that was negative infinity. So what do I get here now? Well, I still get negative infinity on top. And if I substitute in here, well, I got infinity, or it's infinite, but it's negative now. So it's still one of our indeterminate forms. So what does that tell me to do? Oh, apply L'Hopital again. Okay, so I'm going to do an arrow again. I'm going to say, therefore, the limit as x approaches negative infinity of the derivative of the top, which was 2. And the derivative of the bottom was e to the negative x, because the negatives are going to cancel, because you get another negative. Well, now what do we get is we get 2, and then what's on the bottom? Well, as x goes to negative infinity, remember that's e to the negative x, as you're walking this way, as it goes to infinity, and if I take the value of 2 and divide it into many, many, many parts, what do I get? Is actually 0. Okay, and by the way, yes, we got infinity over infinity. Each time was 0. Is it always going to be 0? No. So don't think that is always going to be the case. You can get a non-zero value. All right. So if I do number 4, if I do as x goes to infinity on this one, is I get 0 times infinity, but that's not one of our forms. Okay, so we're going to manipulate this and put this on the bottom and just rewrite it. The limit as x approaches infinity, and I get x squared over e to the positive x then. Okay, so if I start plugging values, or if I now substitute that, well, I get infinity over infinity. Okay, so what does that tell me? I can go apply L'Hopital's rule again. Okay, because by the way, we're going to positive infinity this time. So therefore I get the limit as x approaches infinity of 2x over e to the x, and lo and behold, I still get infinity over infinity. Okay, but I want you to think about which one's actually growing faster. E to the x is, so what should I get? As I should get 0. So I'm going to go apply it one more time. The limit as x approaches infinity of 2 over e to the x, and that does in fact equal 0. Okay, so didn't get a final. We still got a value of 0, but that is not always going to be the case. Okay, all right. Last one I'm going to do. This is not lime, by the way. Neither was this one. Bad joke. Okay. So I'm going to rewrite this again because I'm going to get infinity times 0. So I'm going to rewrite this as the limit as x goes to infinity of the root of x over e to the x. Okay. So now let's take a look at this as well. What happens? Oh, direct substitution. I get infinity over infinity, so I can apply our friend L'Hopital. All right. So I get the limit as x approaches infinity of, all right, this is x to the 1/2. So isn't that 1/2 x, I'm sorry, it's 1/2 x to the negative 1/2 over e to the x. Okay, as x approaches infinity, and I'm going to rewrite this, the limit as x approaches infinity of 1/2 over 2 root x over e to the x. Well, as x goes to infinity, what do I get on the bottom here? Well, I get 1 over infinity, which is 0, divided by infinity is in fact what? 0. So yes, it seems, are we always going to get 0 on these? No. We will get some finite values in some of the latter ones we're going to do. But so this is the first example, or the first set of the L'Hopital's rule. We'll do some more of these in the next video. Okay? Thank you.